Now, vitamins are insanely high yield. I'm going to say it again. Vitamins are insanely high yield. You cannot take your test and not get at least one, if not multiple, vitamin questions. Here's the thing about vitamins, and we're all friends. We've been together 5 days. I think we've got a good rapport. I think we're in the same mindset at this point. Here's the thing. If I'm being honest about vitamins, most questions about vitamins do feel kind of boring because either you know what the deficiency looks like or you don't. And on these questions, when they start talking about vitamin deficiencies, we're going to use niacin as the example. Niacin is one of those vitamins that every med student, every doctor knows because niacin is one of those that everyone loves to discuss. Now, in your book on pages 150, 151, you'll see a large chart or a large table of vitamins. One thing I was able to do for you is, while I can't give you every slide I ever teach from because Kaplan doesn't want it, because I'm using the book basically, I did choose to give you all of my water-soluble vitamin slides because I've tweaked them over the years to be slightly distinctive. Not that the book gives you bad info, because it doesn't. But I wanted to give you a happy medium between what the book says, what other resource like First Aid said, and I'm giving you the joshed up list of, if you know these are the symptoms that are always mentioned in a vitamin deficiency question. So rather than make you copy all of these down, I wanted you to have that handout available so that you could say, this is the joshed up list. If I know this list, I know what every single question he's come across has seen. So that's just from my own nutritional experience. Here's what I've seen. Now, the reason I chose to do that really is secondary, because like I said, when it comes to vitamins, you got to know the deficiency. You got to know what missing the vitamin looks like. This right here, the deficiency pathway, is by far the highest yield. If someone is missing niacin, you need to be able to quickly say, this is the problem I expect. Here's the thing. How many test takers do you know will say, oh, niacin's missing, they're going to get pellagra? Oh, niacin's missing, they're going to get diarrhea, and they're going to get dementia, and they're going to get scaly dermatitis, primarily of sun-exposed areas. Almost everyone. By the time most people go to take their test, they know the deficiencies. If I were to tell you on a USMLE question, patient is missing niacin, which of the symptoms would you expect? That question is going to be answered correctly 90% of the time. Because everyone goes into the test knowing they have to know the pathology. How does the test make it to mask that? Like if every doctor, every med student, every test taker goes in knowing niacin deficiency causes pellagra, how is the vignette, how is the question going to trip you up, or how is it going to trap you? It's never going to say patient's missing niacin. It's going to give you a patient where you have to realize the problem is likely niacin. So that's what I want to fixate on. Even though the highest yield topic is what does it look like when the vitamin is missing. They're going to make you have to look at the vignette and say, it must be niacin. They describe the symptoms or they describe the patient who's missing. Now, if I wanted to give you some clues that it was niacin, I might, instead of telling you niacin, I might tell you why we need it. Niacin gives you or generates nicotinamide. And niacin comes from vitamin B3, or they're the same thing. Niacin, known as also nicotinic acid. So niacin, aka nicotinic acid, aka B3, these are all going to generate nicotinamide. Now, either that nicotinamide N is used on NAD, and we use that for oxidative phosphorylation. When you generate NAD and NADH, that's used in energy. NADH powers electron transport chain. So if I mention that I'm missing a vitamin necessary for oxidative phosphorylation, that could be a clue. We also need the nicotinamide to make NADPH. And what does that P stand for, NADPH? Well, technically, it stands for phosphate. But that doesn't help me much. We're going to pretend that NADP stands for production. Because you need NADP to produce things. If you want to produce biomolecules, you need NADP. It's needed for synthesis of things like fats and cholesterol. If you want to do biomolecule production, you need NADP. Also in your immune system, if you want to fight off certain infectious agents with an oxidative burst, you need NADP to produce that oxidative burst in your immune system. Create reactive species to kill off bacterial infections before they become serious. You need NADP for that oxidative burst. And then even in your red blood cells, you need NADP to reproduce glutathione. Your red blood cells are constantly under attack. They need some help to protect themselves. So by allowing us to reproduce glutathione, red blood cells will be protected. I need niacin for energy, that's NAD, but also for producing things, producing molecules, producing oxygen, that's NADP. And I've seen a lot of questions in my day, actually a lot. I've seen a number of questions in my day that delineated NAD and energy from NADP and production. Now, in reality, NAD itself is kind of useless. You don't make energy from that. NADP is kind of useless. You don't produce anything from that. What you want is the useful version. It's NADH. That's going to help me get energy. It's NADPH. Well, if I can write that, makes more sense. It's NADPH that's going to help me produce things. So in your body, you have a ton of enzymes known as dehydrogenases. You have hundreds of them. What would you guess a dehydrogenase does? Just based on the name itself, what would you guess a dehydrogenase does? Yeah, you would think it moves hydrogens, right? It says dehydrogenase, let's move hydrogens. And that's true. Here's a problem though. Can you really just move hydrogens? Can you really? No. Every time we move something, it needs to be neutral. So if you're going to move positive hydrogens through dehydrogenate, meaning you're going to remove a hydrogen, guess what else you got to move along with it? If you're going to move a hydrogen, you need to move a negative electron along with it. So dehydrogenases exist to move hydrogens and electrons. That's all they do. They find a molecule, steal a proton, hydrogen, steal an electron, negative, and move it. But you can't just release them. If you took off a hydrogen and dumped it, pH would go crazy. If I took an electron and released it, you would create all kinds of damage. You got to have somewhere to put the electron, somewhere to put the proton. And that is primarily where NAD and NADP come in. Niacin is very good at accepting electrons, accepting protons, and that's why it's used by dehydrogenases. Now we're going to come back to this, but I want to tie it together in a little memory. For instance, if someone were to make NADH, if a dehydrogenase moved the hydrogen onto NAD, made NADH. If a dehydrogenase moved the electron, put on NAD to make NADH, how much energy can you honestly generate? How much energy can you generate from NADH? How much ATP? Technically, you generate somewhere around about 2.5. We're going to say that NADH, if you round it, gives you right around 3 ATP. And that's helpful for memory devices. NADH, the energetic molecule that got the hydrogen, got the electron, it's going to make 3 ATP. If you want to make 3 ATP, that comes from NADH, which came from vitamin B3. And if you're missing NADH, if you can't make those 3 ATP, if you don't have B3, guess what symptoms you get? If you don't have the NADH, and if you don't have the 3 ATP from B3, you get the 3 Ds of pellagra. Either you're not getting enough niacin from your diet, or you're not able to synthesize it from your tryptophan. We said yesterday if they're losing tryptophan, they may get the 3 Ds of pellagra, right? Diarrhea, dementia, dermatitis. So 3 ATP from B3. And if you don't have B3, you get the 3 Ds. But what I want to do, and this is where we're going to wrap for our break, one thing I think to really drive this home, and the reason I started with B3, the reason I started here was one thing I like to do in vitamins. It's the same thing I did with amino acids where we did chance, where I said, see this, say that. When you see a dehydrogenase, when you see an enzyme that wants to move hydrogens, which also means if it's moving hydrogens or H plus protons, it's moving electrons, E negative. If you see a dehydrogenase, it needs B3. So I say dehydrogenase, you say B3. There are hundreds of dehydrogenases I could test you on. Do you think it's smarter to memorize all 100 plus dehydrogenases that use niacin? Or do you think I could just learn some of the weird exceptions and then be able to still get every point? Let's learn the exceptions. When you come back from break, we're going to talk about the only 4 that are tested exceptions. Meaning that if you hear dehydrogenase, you think B3. And when you come back, we talk about which ones are missing, and the ones that are missing, we'll finish up. Or which are actually missing. We finish. It's break time, and my mouth wants to tie on itself. So when you come back, we're going to say B3, you say dehydrogenase. We're going to find the 4 exceptions, so you know exactly which enzymes your board is mentioning to try to make you think, is it pellagra or is it something else? See you guys back in here in 10 minutes after our very first break of the day. so I think it's absolutely worthwhile mentioning. And I was kind of saving it up because I wanted to transition. Notice here, I didn't mention any explicit enzyme names other than dehydrogenases. Dehydrogenases in general take an electron and a hydrogen from some molecule, and they just move it and put it somewhere else, right? Just happens that NAD, made from niacin, or NADP, made from niacin, that's a good place to put hydrogens whenever they've been moved from somewhere else. Or that's a good place to put electrons when we move them from somewhere else. But I mentioned before, I say dehydrogenase. I say enzyme that's stealing electrons and hydrogens and moving them. What vitamin do you immediately say? I say dehydrogenase. And you're going to say what? You're going to say B3. You're going to say niacin. Now, the thing is, when we talk about dehydrogenases, they're usually named for what they steal from, not what they give to. For instance, pyruvate dehydrogenase. Guess what pyruvate dehydrogenase is stealing from? Guess what it's removing hydrogens from? Guess what it's moving electrons from? It's removing it from pyruvate. So literally, we'll watch as the electrons go from pyruvate. We'll watch as the protons go from pyruvate, and eventually they're going to end up on niacin. That's how dehydrogenases work. You steal from one molecule, move to the other. Dehydrogenases are generally named for what they steal from, or where the electrons and the protons were removed from. They're named for their substrate. That's where we get the terms dehydrogenase. However, I said, how many special dehydrogenases are there? There are 4. There are 4 dehydrogenases that are special in that they don't require only niacin. Now, in reality, just between us, there are actually a lot more than 4. So what I keep saying is, on your USMLE, there are only 4, because who cares about the others? If I'm not going to get a point for it, I'm not going to make you memorize some random enzyme. That's crazy talk. If I haven't personally seen it asked on questions, I'm not going to make you think about it, because if it's not in UWorld, AMBOSS, QBank, it's not in DIT RX, it's not been on NBME, if it's nowhere in existence, I'm betting no one's ever seen it. 4 is plenty. Let's make sure we just fix it on getting ready for the test, right? We don't need to be a world expert. We just need to be a step 1 expert. But we said there were 4. Now, one of the questions that came in about these 4 special dehydrogenases is, do they not use niacin at all, or do they just need more than niacin? And the answer is technically both. For instance, if you look at the thiamine list, now the person who's going to be thiamine deficient is most likely an alcoholic. And that's because, and that's what MCC stands for, most common cause. So the alcoholic, the alcohol metabolites in particular, alcohol metabolites are going to bind to and inactivate thiamine. Therefore, you run low on thiamine. Now, if you don't have thiamine, you might see Wernicke and Korsakoff syndrome, where Wernicke might lead to some of the eye issues, the acute psychosis, maybe some nystagmus and ataxia. But if it progresses to Korsakoff, now I'm getting longer-term brain damage, memory issues, confabulations. If you were to do an autopsy on someone who died from a thiamine deficiency, what would you notice in their brain? If I were to do an autopsy on someone who's died from Wernicke-Korsakoff syndrome, I'm going to see some mammillary body degeneration. I'm going to see some gray matter problems between, say, the 3rd and 4th ventricles, the mammillary bodies, absolutely. We see lots of atrophy of mammillary, perfect, which makes sense. The longer you go without thiamine, the more necrosis, the more atrophy I see, the more problems we're going to elicit, the more problems we may anticipate. It's one of those hallmarks of Korsakoff, that we see very specific necrosis or very specific atrophy in the brain. Now, if you are B1 deficient, you don't always see Wernicke-Korsakoff. You don't always see the memory issues, the confabulations, the ataxia, the eye issues. You might get beriberi as well. And that's actually a pretty common question, where they give you symptoms of a deficiency. You have to figure out which vitamin is missing, and then they ask you what other effects could be seen in a similarly deficient patient. For instance, if I were to describe Wernicke-Korsakoff in a patient, you'd say they're missing thiamine, B1. And I always remember thiamine, I call it thiamine. It's mine, M-I-N-E. It's all about me. And let's face it, we're all pretty egotistical. So if it's all about me, I'm number one. B1 is all about me and mine. But if someone were missing B1, if they were missing thiamine, and they didn't get Wernicke-Korsakoff, then they might get beriberi, where either it's just going to be dry and basically target the neuropathy, the nerves, or it could lead to some heart failure and fluid retention, some edema, and we term that because of the fluid. We call that the heart failure. We call that one wet versus dry. So it's important that you recognize not just one symptom of a deficiency, but that you're able to recognize that patients who have this deficiency can have a variety of different pathologies that may illuminate them. Now, this is the part everyone remembers. If someone's missing B1, we expect the Wernicke-Korsakoff. We expect the beriberi. Fine. However, if I wanted to twist at you, I'd ask you which enzyme doesn't work. And notice, how many enzymes require B1? How many different enzymes did I list require thiamine? Well, 4 of them. Notice anything special about 3 of these thiamine containing, requiring, won't work in an alcoholic patient enzymes? 3 of them are dehydrogenases. Now, whoa. We just said 3 of them are dehydrogenases. What vitamin should you immediately think of? I say dehydrogenase, you say B3. Here are 3 of the 4 special dehydrogenases. These are 3 of the 4 special dehydrogenases. These 3 are special because they need not only niacin. Now, they do need niacin. They, in fact, need thiamine for their structure, so they need B1. They need riboflavin for their structure. They need B2. They need niacin because the electrons and hydrogens got to go somewhere. And niacin, which creates or leads to NAD, will be happy to take the electrons from them. They're going to need something called pantothenic acid, or B5. And they need something called lipoic acid. They're going to need those 5 things. Now, what I did to memorize these 3 enzymes, whether it's pyruvate dehydrogenase or alpha-ketoglutarate dehydrogenase or branched-chain keto acid dehydrogenase, those 3 special dehydrogenases, no matter which one it is, of those 3 special the way I memorized it is I literally counted, well, these 3. Pyruvate, alpha-ketoglutarate, branched-chain, those 3 special dehydrogenases, I literally just said they need 1, 2, 3, 4, 5. B1, B2, B3. Now, there's no such thing as B4, but you know it has 4 letters, acid. So B4 made me think of lipoic acid, and then B5. 1, 2, 3, 4, 5. Some people don't like that kind of mnemonic. Another way to memorize, and this is one of the few memory devices Kaplan actually puts into the book, and actually works pretty well, is these 3 are so special, they need something extra. They need a little bit of extra love. So these 3 dehydrogenases are sometimes said to be requiring what we call tender loving care from Nancy, or maybe tender loving care from Nick. Or by the time you take your test and everyone's bugging you, tender loving care from nobody, you want everyone to go away. I don't really care which name you throw the in there. But these 3 dehydrogenases need tender or thiamine, that's the T, lovin L, that's lipoic acid. CARES technically stands for coenzyme A, but coenzyme A comes from B5. Riboflavin, that's the that's the F, or that's B2. And then Nancy or Nick or nobody, that's the niacin, that's the N. Now, I saw that someone mentioned or asked about tetrahydrobiopterin. For THB, that for your test purposes, only remember THB for making neurotransmitters. You need THB to make things like dopamine. You need tetrahydrobiopterin to make things like serotonin. You need THB to make almost all of your neurotransmitters. But if you get a question on your test about tetrahydrobiopterin, it's probably making tyrosine, making dopamine, making things like that. It's a good question to bring up there. For these 3 dehydrogenases, they're specifically going to need these 4 vitamins, that cofactor. Tender love and care from Nancy, or tender love and care from Nick. They need something extra, something special. So in an alcoholic, none of those would work. But if you have someone who suffers from Wernicke-Korsakoff syndrome, do you go and test their pyruvate dehydrogenase? No. Do you go and test their alpha ketone? No. What enzyme do you test for a thiamine deficiency? Well, you test transketolase. And there are 2 reasons for that. One, if I were to look at pyruvate or alpha ketoglutarate or branch chain, one, those need lots of vitamins. So if I have no B1 or no B2 or no B3 or no B5, none of those would actually work. And that wouldn't be very selective for B1, where Wernicke-Korsakoff is caused by a B1 deficiency. So if I want to test for a specific B1 deficiency, I should use a selective B1 enzyme. That's an enzyme called transketolase. Although I always write it, even to this day, if I'm writing it out in like an email, I have to catch myself. I'll write transketo and change the L to 1 to remind me that transketo 1-ase is the only one that needs B1. So if I want to test you for a B1 deficiency, even though 4 vitamins won't work, I'd rather test you on the selective enzyme. So if I want to study if you're missing B1, let's look at the one that needs only 1, or transketo-1-ase, transketolase. The second point to that too is most of your dehydrogenases tend to be in the mitochondria, which makes sense. If you're going to move hydrogen, if you're going to move electrons, if you're going to make energy, where should you make NADH if you want to generate energy? Where should you be moving electrons if you want to generate aerobic energetic process? I need to do it in the mitochondria. The mitochondria is the powerhouse. That's where electron movement will occur. That's where I can generate. But if I want to study transketolase, that's cytoplasmic. Can you study, so if I take a red blood cell, if I take a blood sample, can I study pyruvate dehydrogenase? No, red blood cells don't have mitochondria. If I take a blood sample, can I study alpha ketoglutarate dehydrogenase easily? No, red blood cells don't have mitochondria. That's another benefit for transketo 1-ase. It's cytoplasmic. So by looking at transketolase, that's the one that only uses B1, so that'll be deficient only if thiamin's missing. And because in the cytoplasm, I can look at a red blood cell and study it. I don't need to do a mitochondrial assay. It's all about location. That's going to be something we talk a lot about today and tomorrow. Is it cytoplasmic? Is it mitochondrial? Because that's a huge clue that your USMLE uses to delineate which enzymes go where or which pathway you may be discussing. Now, and I like that. You could see, and you could theoretically get a question about infantile beriberi. I think, and the question I see in the chat, I've seen that one example. I've not seen enough that I put it in my present and the long slides. But if you do another question, it's definitely not something you would not come across. So that's a nice little thing to add in there. How many special dehydrogenases are there? 4. How many have we learned? 3. 4 special dehydrogenases in general that need something extra. But we've got 3 of them. 3 of the 4 needed more than B3. 3 of the 4 special dehydrogenases needed B1, B2, B3, B5, and lipoic acid. They need the tender love and care. But we're missing one. The missing one is one called succinate dehydrogenase. Now, it's rare that you ever see succinate dehydrogenase called that without its old name. Succinate dehydrogenase is also known as complex 2. Guess which vitamin succinate dehydrogenase or complex 2 is going to require? It's going to require vitamin B2. So riboflavin or vitamin B2 can also generate an electron and proton acceptor. You use B2 to create the flavin portion of FADH, or that flavin protein. And we know that if you were to generate FADH2 in the mitochondria, how much energy in general do you get from FADH2? You get about 1.5. If we round it, it's going to be really close to 2 ATP. Thus, a nice little memory device. FADH2 will lead to 2 ATP, so it must have come from vitamin B2. And hint, what's the only enzyme Borg tested to generate FADH2? What was the only dehydrogenase that needed only B2? It was complex 2, or that succinate dehydrogenase. That's the fourth special dehydrogenase. Because if you look at the handout, if you look at the book, I said for riboflavin, for B2, you need it for dehydrogenases, but we need it for all the ones that needed thiamine. So pyruvate dehydrogenase, alpha-ketoglutarate, branch chain dehydrogenase, all of those three that needed thiamine, that needed tender love and care from, if they needed B1 as a dehydrogenase, then they needed B2. But succinate dehydrogenase is special in that it needs only B2. It's special in that it needs no B3. So I say dehydrogenase, you now know the 4 weird exceptions. There are 3 that need more than B3, and then there's succinate dehydrogenase or complex 2, specifically designed to generate FADH2, which in your mitochondria would generate 2 ATP, and that would create, or be created from rather, riboflavin or B2. Those are the 4 special. If it's not one of those 4 dehydrogenases, then it's not special. All the others just need niacin. 3 needed more than niacin, 1 didn't need B3 at all. Succinate dehydrogenase does not use B3. Succinate or complex 2 only wants B2, no B3. Those are my 4 big specialties. Now, if you look at the deficiency, riboflavin deficiency is kind of rare to see, except on test day. But do you notice anything in common about the symptoms or the pathologies we tend to see in the patient who's missing riboflavin? We see lots of epithelium, but go one step further. We'll go one step further. Corneas, lip cracking, mouth problems, tongue problems, facial and scalp dermatitis. It's all your face. Almost everything riboflavin related is head related. Corneal neovascularization, cheilosis, and cracking and scaling of the corners of your lips, or stomatitis, mouth issues, a weirdly colored tongue. Seborrheic or facial dermatitis, scalp-related, face-related dermatitis. So the way I've always remembered riboflavin deficiencies is I hear riboflavin and I think riboflavor. Where do you get all of the flavor? Or where do you find flavor on the human body? Mouth. Where's your mouth? Your head. I've never missed a riboflavin question with that little memory device in my mind. A patient has nothing but head and mouth issues. That's all about the mouth. That's all about the head. That's where my tongue is. That's where the flavor is. I think head, I think mouth, I think tongue, I think flavor, I think riboflavin. They can also be anemic, but they'll never, and this is the Adams 20, they'll never mention just the anemia. There's always going to be these other things. So if you get a lot of head issues, the rest of it's not as important, I don't think. Because if they're going to mention some of that other weird stuff, they're going to have to give you the head issues. As anemia itself can be caused by all kinds of things. But if I see like an anemia and they mention cracking and scaling of my lips and neovascularization, say the scalp dermatitis, they're always going to give you the riboflavin stuff. And here's the thing about all of it. When it comes down to your there obviously, this is not a list of every deficiency that could be there, but I'm trying to give you enough of a pattern that you're not memorizing 40 different things, but you know kind of what to look for as much as possible. These friendly flavins, if you will. These friendly flavins. Now let's finish it off with B5. Now B5 is used in all kinds of enzymes. If I say B5, you say CoA. B5 yeah, CoA. Literally, pantothenic acid, which I've always called pentothenic acid, because let's face it, if you call it pent is the chemical prefix for 5. So pentothenic acid must be B5, that's fine. But the reason we even need B5 is that's where you get coenzyme A from. That's really just a carrier. How many pathways utilize coenzyme A in some way, shape, or form? Yeah, tons of them. Now, we know 3 of them off the top of our head. We have pyruvate dehydrogenase. That's because it makes acetyl-CoA. So we know there are at least 3 dehydrogenases that need B5 because you use CoA in them, like pyruvate dehydrogenase made acetyl-CoA. However, note there are tons of pathways that utilize coenzyme A somehow. Do you think it's worthwhile to memorize every pathway that utilizes coenzyme A? No. If they want to test you on B5, they're going to literally show you a diagram. And they're either going to show you that coenzyme A was added, like pyruvate dehydrogenase added coenzyme A. Or they might show you a pathway you remove CoA. Like there's an enzyme which is kind of weirdly named succinyl-CoA synthetase. It turns succinyl-CoA into succinate. What's missing? What does succinyl-CoA synthetase do? It cut off the CoA. So if I wanted to test you on B5, I would give you a diagram, and I would ask you where was pantothenic acid needed. And you would either look for a step where coenzyme A was added, which means the step used B5, like pyruvate dehydrogenase adds coenzyme A to make acetyl-CoA. Or alpha-ketoglutarate dehydrogenase adds CoA. Branch chain keto acid dehydrogenase adds CoA. That's why all those pyruvate, alpha-ketoglutarate, branch chain dehydrogenases, that's why all those special dehydrogenases needed B5. They all added CoA. Or I could show you a step where CoA is removed, and you know that's a step that removed B5. So in the long run, outside of those weird 3 special dehydrogenases that needed tender love and care for Nancy, don't try to memorize every B5 requiring enzyme. There are too many. You use coenzyme A as a carrier quite a lot in your system. Comes from, you use CoA quite a lot as a carrier in your system. So don't memorize the CoA using enzymes outside of those 3 special dehydrogenases. The key is, if you see CoA was added, you used B5. If you see CoA was removed, like in this pathway where succinyl-CoA became succinate, if you see CoA is cut off, you know that step removed B5. That is literally the only ways I've ever seen pantothenic acid tested. Is looking at a pathway, looking at enzymes, saying, oh, you're adding CoA, add B5. You're removing CoA, remove B5. That's literally how I've always seen it tested. Because in all fairness, Not a lot of people are B5 deficient. I'd be fair to say that you don't need to memorize any pathology for a B5 deficiency. Because as long as you eat food, like as long as your diet is not just like lead paint and hugs, like as long as you're ingesting something that's made of food, even processed food, almost everything has a little bit of B5 in it. So even though there's a possibility, this is just not one of those I think you need to worry a whole lot about in terms of sickness. If they're going to give you B5, what are they testing you on? I say B5, you say CoA. Add B5 and you use CoA, or add CoA and you use B5. Remove CoA and you removed B5. So you hear B5, think CoA. Either you're adding it, you're removing it. We know some enzymes that are special, but we're not going to memorize any extras because there's nothing beneficial from that. So we did all the B1, B2, B3, B5 together because I think it's nice to think about all those special dehydrogenases. B6 or pyridoxine is kind of a special one in that pyridoxine itself is kind of useless. If your body wants to use B6, then you have to convert it to pyridoxal phosphate. So you have to activate it. That's done by a kinase. So pyridoxal phosphate, that's the active version. PLP is what you need if you want enzymes to work. However, there is a drug that we currently use that blocks this kinase. There's a drug we currently use that prevents activation of pyridoxine. What drug is known to inhibit activation of B6 and is therefore the most common cause of a B6 deficiency? The most common cause is going to be someone who takes isoniazid, which is usually abbreviated INH. Someone's either trying to prevent or treat tuberculosis, they're on isoniazid. Isoniazid works against TB, but as a consequence of its structure, it's able to mess with your own B6 activation. So what do we typically give with isoniazid to prevent excessive side effects? Yeah, you give pyridoxine. As long as I give you plenty of B6, I'll be able to activate enough of it and I can prevent this deficiency. Isoniazid alone will inhibit activity of B6, but if you put them together, then B6 will become active because there's just so much B6 to outcompete. So you see those things. I think in your test, the most likely scenarios of an isoniazid deficient patient, or the most likely problems you get in isoniazid, there's going to be a number of liver issues, and that's probably because without B6, your aminotransferases don't work. Like if someone's having a liver function test done, what enzymes do you look for in a liver function test to see if the liver is fun? You look at things like AST, ALT. That's because they're very common in the liver. They should stay in the liver. But you know what? Those enzymes, AST, ALT, to work, they need B6. So not surprising if B6 is missing, your liver doesn't function completely normally. Okay, that's fine. Some more direct things, though, that you'll get, without B6, you can't make heme. And that could be a problem. Without B6, the very first step of heme synthesis is inhibited. Without B6, you cannot use aminolevulinic acid synthase. And therefore, cells or precursors that need heme won't ever make it, which means iron can't go into heme. If you don't make heme, there's nowhere to put the iron. Where does iron tend to accumulate in a precursor cell if there's no heme to eventually put it in there? They accumulate, yeah. If you don't make heme, then iron will start to accumulate in the mitochondria. And what happens to the mitochondria if iron accumulates because no heme was being made? It might start to deposit. You might start seeing these little rings around the nucleus, little Fe rings. You get the sideroblastic rings. You could end up with sideroblastic anemia, or these ringed cells. What other poison is known to lead to sideroblastic anemia? outside of B6 deficiency is also lead. Why? Well, because lead also inhibits heme synthesis. So if I have no B6, you can't make heme. Iron accumulates in the mitochondria. You might start seeing these ring sideroblasts. Lead inhibits heme synthesis. And we'll talk about where lead inhibits on Monday. But lead also inhibits, and with lead, you're going to end up with iron accumulating in the mitochondria. You get these ring sideroblasts. So notice, with sideroblastic anemia, that's usually a heme problem. Either you're not making it, or either there's no vitamin to make it, or you're purposely inhibiting with a toxin. But without the heme, there's nowhere to put the iron. It accumulates in the mitochondria. And so you end up with these weird precursor cells that have all kinds of problems. The one that your book doesn't mention, but I think is worth adding, is going to be that you also need B6 to metabolize homocysteine. Now, this is from yesterday. Where does homocysteine actually come from? Like, it's not something we just generate randomly. It's a byproduct of methionine. Methionine good, methionine great, methionine awesome. But methionine, once it's metabolized, it becomes homocysteine. So that's why I'm calling this methionine metabolism, even though one of my animations for some reason didn't quite pop up the way I meant it to. It's okay. So when you generate homocysteine, we have to get rid of it. The majority way, or the major way to get rid of homocysteine, is to convert it into something called cystathionine. By converting it into cystathionine, you make it safe, you make it excretable, you make it tolerable, but that requires vitamin B6. So if B6 is missing, what's going to happen to your homocysteine levels? If there's no B6, you're going to see more and more homocysteine. It's going to increase, it's going to rise, it's going to build up. Not good. So without B6, you can't metabolize homocysteine. And if you can't metabolize it, it might start getting in the urine. What happened when cysteine accumulated in urine? It started making some stones. It started reacting weird. Guess what homocysteine will start to do? If it ends up in the urine and it really starts to accumulate, it might become somewhat problematic as well. Homocysteine's in the urine, that's a different environment. They'll start linking to each other. They'll create their own little disulfide links. We might call it homocysteine. And rare, but it's possible. So notice you're definitely going to see homocysteine in the blood. You might see homocysteine in the urine. If much has accumulated, you get the sideroblastic anemia. Now notice B6 may cause some mouth issues. What other vitamin may also cause some lip cracking and some mouth issues? Could also be B2. That's why I'm saying don't look at one symptom and just go whole hog. I need the whole picture. If I'm going to pick B2 causing mouth issues, I better see some head issues like seborrheic dermatitis or scalp-related issues. I better see some eye issues, better see some tongue issues. If it's mouth and more head, that's riboflavin. But if I wanted to point you toward B6, I might mention the cholosis stomatitis. I might mention homocysteine. I might mention the sideroblasts, because you know if there's sideroblasts, you're not making heme, and that would be a good B6 issue, because without B6. So look at the whole picture before you figure out which specific vitamin is or is not present, or which vitamin is missing or not. The reason I harp so much on homocysteine here, though, is when I say homocysteine, almost no one thinks B6. And that's because, and if you don't, then you end up going down a wrong pathway and you pick a vitamin that's unrelated. Which vitamin do you typically think of if I mention homocysteine is a problem? Or what vitamins do you typically think of if homocysteine recycling is a problem? You think of folate, you think of B9, you think of cobalt. But that's because there are two ways to get rid of homocysteine. B6, along with serine, carries out homocysteine's metabolism. B6 will help you forever get rid of homocysteine, make it safe cystathionine. B6 will help you metabolize and eliminate. But B9 and B12 are going to help as well because homocysteine is so dangerous. We need not one, but we need two we need two pathways to get rid of it. So we're going to come back to this story about homocysteine and B6 once we talk a little bit more about folic acid. Thing is, B12 is insanely high yield. But I can't do B12 until we've done biotin, which technically is the very first one that your book lists. Now, the high yield chant we're going to use for biotin is I say biotin or B7, you're going to say carboxylase. Literally every enzyme tested on your exam for B7 is what we call a carboxylase enzyme. Literally, the whole job of a carboxylase is to add a single carboxyl group, is to build things. Now, some people like the memory device that carboxylases are as easy as A, B, C. They're as easy as A, B, C. And Mariana, yeah, any enzyme I put in my table, you have to know those. Especially if we talk like cystathionine synthase, we spent that extra time talking about it, or the aminolevulinic acid synthase. Oh yeah. Now I didn't put every enzyme, but I put the ones I think you'll be tested on. So I've tried to make it as short as possible as it comes to enzyme lists. But you definitely want to know the enzymes I put in your handout or the enzymes we're talking about, without a doubt. I think that's a good question to ask. But a lot of people for carboxylases, like the memory device, they're as easy as ABC. Because literally every carboxylase on your test is building something. Like how many of you have heard someone at some point in your life say, the greatest journey begins with a single step? Or the greatest building starts with a single brick. Everyone's probably heard one of those platitudes at some point, right? Well, not to be put too fine a point on it, but the building of any great carbon structure begins by adding a single carbon. For instance, pyruvate carboxylase is going to add a carbon. Guess what you're going to add a carbon to with pyruvate carboxylase? Yeah, you're going to add it to pyruvate. Now, here's my question. Why would you ever build pyruvate? Why would you ever want to make pyruvate bigger? Why would you ever want to add carbons to pyruvate? And we talked about this yesterday. That's gluconeogenesis. When you are well-fed, we said yesterday that when you are well-fed, you turn glucose into pyruvate. When you're well-fed, you want to burn sugar. You do glycolysis. But remember the first tenet of biochemistry. Everything's reversible. So if I'm well-fed, let's turn glucose to pyruvate. If I'm poorly fed, let's reverse it. Let's turn pyruvate back to glucose. Now, pyruvate came from alanine, because if we're starving, our muscle releases alanine, or we'll make pyruvate. But if you want to build glucose, you have to add carbons. The building of any great glucose starts with a single carbon. So pyruvate carboxylase, very helpful in gluconeogenesis. You make pyruvate when there's lots of sugar, so let's build on pyruvate when we're missing sugar. Win-win. Same thing is technically true with acetyl-CoA carboxylase. Now, this one's a little bit harder because we didn't talk about this one yet. But whenever you are poorly fed, what is the primary energy source of the poorly fed cell? And the question, we only use B7 to build on pyruvate, so we only used it for gluconeogenesis. It wasn't used to breakdown, like glycolysis is breakdown. That's not building anything. So B7 was needed to build, not breakdown. We need it for pyruvate, building, but not glycolysis. So what do we use? I see people saying we're using ketone bodies, but the ketone bodies come from fats. Thing is, when you're poorly fed, you are going to turn fatty acids into acetyl-CoA. So what's going to happen if you're well fed? If when you're poorly fed, you are metabolizing and breaking down fatty acids into acetyl-CoA. What should happen in reverse? Or what should happen if you're well fed? If you're breaking down fatty acids when you're poorly fed, you should make fats if you're well fed. Makes sense. What are you going to make fat from? You're going to make it from acetyl-CoA. Pathways are reversible. If a poorly fed person turns fat into acetyl-CoA, then a well-fed person should do the opposite. Let's turn acetyl-CoA back into fatty acids, because that's that first tenet of biochem. When you go, or when the scenario is changed, when the pathway, when the environment reverses, pathway should flip. A poorly fed person burns fat, makes acetyl-CoA. Thus, a well-fed person should turn acetyl-CoA back to fat. But acetyl-CoA is really tiny. It's only 2 carbons. Fatty acids that we generate tend to be 16 carbons. What kind of enzyme are you going to need if you're going to start the great fat journey of a 16-carbon structure? What's going to be important? It's going to be a carboxylase. If you want to build a carbon structure, any great carbon structure, which in our body, the 2 great carbon structures are glucose and fat. If you want to build any great carbon structure, it starts with the addition of a single carbon. The greatest journey starts with a single step. The greatest monument starts with a first brick. A great carbon structure begins with a single carbon atom. And that's where these carboxylases come in. Now, the reason we call them A, B, C, and it makes sense, right? Whenever you're burning things, to reverse it, you need to build. To build requires biotin. To build requires that carboxylase. To build requires adding that very first carbon. Now, the reason we call them ABC is that whether it's pyruvate, whether it's acetyl-CoA carboxylase, it requires 3 things. To build anything requires energy. So the A means ATP. B stands for biotin. That's B7. And C stands for CO2. Now, this is a perfect example of another rule of metabolism. Do we like to waste things? Do we like to throw carbons away? No. Our body was designed to be this lean, mean, green machine, in that we want to recycle. We want to keep the carbon. Carboxylases are a perfect example. They literally take carbon dioxide that you would have just breathed out. They get carbon dioxide that you have just exhaled. And instead of you wasting that single carbon, carboxylases grab it, add it, and use it to rebuild energetic molecules. They're going to use it to build glucose when you're starving or build fat when you're well-fed. But if you don't have B7, you can't build. It's going to hurt you when you're fasting. It's going to hurt you when you're well-fed. Without B7, you can't build the right structures. And those problems are normally seen as hair loss. You get some bowel inflammation. You get some skin issues. But I got to be honest. How many B vitamin deficiencies cause dermatitis? How many B deficiencies lead to skin issues? Almost all of them. B2 cause facial dermatitis, B3 cause dermatitis, B7 cause... Dermatitis is really not the world's best symptom because almost every B deficiency leads to some level of dermatitis. That's why we're not ever focusing on one symptom. If you memorize one symptom for one vitamin, you're going to miss so many questions. That's why I'm trying to give you the whole path. Not everything, but specifically the whole picture that I think most questions will present. So dermatitis means it's probably a B vitamin, but I want to look at everything else that's there before I say it's got to be this one or that one. If they've got skin issues and hair loss, that's B7. or if they've got hair loss and some bowel issues, maybe that's probably B7. Although usually in a vignette, B7 is hard to run out of unless you don't absorb it. And the only people who don't absorb biotin are people who drink raw egg whites. Turns out in a raw egg white, you have lots of a protein called avidin. And with avidin, that's going to bind up the B7 in the gut specifically. And by binding the avidin in the gut, you can't absorb it. So if someone's eating raw egg whites with their avidin, you're going to end up with B7 getting stuck in the gut. You might get your hair loss. You might get the bowel inflammation and the like. So I think the B7 story makes a lot of sense, right? It's all about building. When you're poorly fed, let's build glucose from pyruvate. When you're well fed, let's build fats from acetyl-CoA. But building requires one carbon. Did we talk about every enzyme here? Have I mentioned every single enzyme that was listed? I did not. I left out the last one. And believe it or not, the last one is probably the one that's going to drive you the craziest. And I purposely chose to take the break here because this enzyme, propionyl-CoA carboxylase, is going to play a big role in a few minutes. Guys, I have a few questions about distinguishing B6 from B12. And this enzyme is going to help us indirectly do that. Now, prop-CoA carboxylase, what does the term prop usually mean? When you talk about chemistry and prefixes and nomenclature, the term prop always means 3. So propionyl-CoA is a 3-carbon molecule. Do you think we should just throw it away? Prop-CoA is a 3-carbon molecule we generate through metabolism. Should we just throw it away? No. In its form, prop-CoA isn't usable. But if we build upon it, we could make it good again. If we build on prop-CoA, we could recycle it, we could regenerate it, we could reuse it. That's all good. So here's your question. If you're going to build on prop-CoA, what kind of enzyme is going to start this process? If you're going to build on this carbon molecule that we can't use, how am I going to build on it? Let's start with a carboxylase. That's where we get prop-CoA carboxylase. Take a little ATP, take a little biotin, take a carbon. We can make it so that we put everything together and build on prop-CoA. Now, here are the two things. And this is what I want you to think of first versus second. Where on God's earth do we get prop-CoA from? Well, that's a good question. Technically, it's a leftover molecule. Prop-CoA is what you get when you metabolize vomit. Now, what do I mean by vomit? Vomit is an acronym. You get prop-CoA when you metabolize valine. So when you metabolize valine, it becomes this 3-carbon chain that is unusable but needs to be recycled. You also get propionyl-CoA when you metabolize an odd number carbon fatty acid. So if I could do an odd carbon fatty acid metabolism, you get a little bit of prop-CoA. With methionine metabolism, believe it or not, as you go through methionine metabolism, eventually you generate prop-CoA. The I stands for isoleucine, the T stands for threonine. But these are 5 molecules that, if I don't need them in their current form, I like to recycle. They're all going to be turned into prop-CoA. So valine, the odd chain fat, methionine, isoleucine, threonine, they all become prop-CoA. Prop-CoA, though, is useless in its current form. Do we want to throw it out? Do we want to get rid of it? Do we want to just say, hey, look at all this valine we turned into prop-CoA, and let's throw it away and waste it. Look at all this methionine we turned into prop-CoA, and let's throw it away. No, let's recycle it. So we're going to add a little carbon to it. That's going to be that carboxylase. That's going to be B7 related. It's going to need A, B, C because it takes some energy. It takes some biotin. It takes a carbon dioxide to do this. And that's going to lead us or generate methyl malonyl-CoA. Now, that in itself is also a problem because when you put that carbon, when you add the carbon and go from 3 to 4, when you throw that methyl group on there, it's in the wrong spot, and that's useless as well. So you'll notice in your handout, I specifically mentioned this is the part 1 of vomit pathway. We're going to come back and talk about part 2 after the break. Because imagine there's no biotin. What molecule would accumulate in a patient who's drinking raw egg whites? What molecule would accumulate in a patient who is ingesting avidin, which is binding their B7 from diet and preventing absorption? If there's no B7, you would expect there'd be lots of prop-CoA. So propionic acid is a symptom or a sign that you're missing B7. Because if there's no biotin, one, you can't build on pyruvate, but you'll use pyruvate elsewhere. That's not a very good clue. And if there's no biotin, you can't build on acetyl-CoA, but that's not a very good clue because you can use acetyl-CoA elsewhere. The best clue for biotin is this prop-CoA. You can't use that. If you can't build on it, it accumulates. And as it accumulates, it is an acidic molecule that will lead to an acidosis. It causes all kinds of problems, but it's closely related to a lack in B7. Because without that biotin, you cannot add a carbon to go from 3 carbon prop, or 3C, to 4 carbon methyl malate. So if there's no B7, you get the prop-CoA. Now, like I said, methylmalonyl-CoA is useless as well, but we'll talk about that after the break when we do part 2 of vomit, as it's going to tie the last little tidbits together, and we're going to leave the water-soluble vitamins and then do some practice questions. So I'll see you guys back in here after the break in 10 minutes to continue our fun discussion of vomit. See you guys again after the break. Chat here. If you're looking for other reasons for biotin deficiency, you get a little bit of biotin from your gut bacteria as well. So even though I think on your test, the most common question or the most common person missing out on biotin will probably be the person eating raw egg whites. If you're on an oral antibiotic or if you're messing with your gut flora, that can definitely mess with biotin as well. I think that's a nice little thing I just read in the chat. Like, I should mention that, or I read in the questions. I should mention that. So as we come back, so notice, we just talked about carboxylases. Fact is, when it comes to carbons, we need to transform them from time to time, or we just need to build usable molecules. And what I mean by the term usable or useless, as I wrote here, is usable carbon skeletons are able to be used in multiple processes. Like if you can make glucose, that's usable in all kinds of pathways. Or if I can make fatty acids, that's usable. With the vomit pathway, and we haven't quite finished it, this is like the little preview. So if we don't follow or don't know all of it, and well, a lot of the questions that came in are actually really good, because they're about what happens next or what moves forward. With prop-CoA, and this is the rule, this is where so much of biochem is where you have to understand it versus memorize it. When you have carbon skeletons, you have to transform them because you can't, if you can't use them in one form, you got to make them something else, right? Like valine is very helpful in translation, but if you don't need to do translation, do you just want valine to sit around in your body and wait? Or if I don't need valine to make a protein right now, do I just want the valine to sit around and say, no. The whole point of your body is if you can't use the carbon skeleton in the form that it's in, let's transform it into some other usable form. Why let something go to waste? So when you have lots of excess valine or lots of excess methionine, isoleucine, threonine, rather than just let them accumulate and eliminate them because you can't use them as they currently are, we're going to metabolize and transform them. We're going to try to turn those carbons of valine and methionine from one form into another. You can't use them as isoleucine. Let's make it useful. The problem with that is to transform these vomit-like molecules, you got to turn them eventually into prop-CoA. Your body can't use that in any pathway. There's no extra path that says, give me that prop-CoA. So you've got to transform it. And that's what the vomit pathway is there for. Taking metabolite products that can't be used and trying to find a way to use them again. Now, that being said, we're going to talk more about the vomit pathway. We're going to add that last little bit to it once we finish, but we're not quite done yet. I like having this as a preview because I think if we did this all, because normally this would be on Sunday. If I waited till Sunday to dump vomit on you, you would have every, that came out. If I waited till Sunday to dump the vomit pathway on you, then you would have every right to throw things at me. But I want us to finish it. We're going to see it again. I'm not going to vomit. Mildly better. There's no good day to dump vomit on anyone. But let's figure out a little bit more about it. Now, to finish up vomit, we got to do two more vitamins. One of those vitamins you talk about is folic acid. Now, who is going to be deficient in folic acid? Who is going to be deficient? Usually it's either going to be a pregnant woman or it's going to be an alcoholic. Alcohol metabolites bind and inactivate folic acid, so you can't use it. Pregnant women need tons of folic acid. In reality, folic acid or vitamin B9 is not terribly useful in the form that we find it. Folic acid needs to be activated, and that creates what's known as tetrahydrofolates. So tetrahydrofolates are used. They're the version of folic acid that a natural human cell can interact with and utilize in relatively important pathways. Okay? Now, if you look at the enzymes that use tetrahydrofolates, what do you notice we use tetrahydrofolates for? Yeah, we use them for bases. We use usable tetrahydrofolate to make thymidines. So you need folates to make T, or the thymidine nucleotide. We need tetrahydrofolates to make purines. You need it to make adenosine. You need it to make guanosine. So technically, 3 of the 4 nucleotides in your body are needed, or rather, 3 of the 4 nucleotides in your body for DNA synthesis require tetrahydrofolic acid in some way, shape, or form. Here's my question. Or I should say question, here's a statement. If you're missing folic acid, then that means you can't do nucleotide synthesis. And that's going to lead to cell division problems. And we kind of talked about this in molecular, but I think it's worthwhile mentioning again. If you don't make thymidine, adenosine, guanosine, cells are going to try to divide, but they can't. Which means they're going to get stuck. Their cytoplasm is going to grow, but their nuclear division isn't going to happen. What do we typically see in cells? If they can't quite finish cell division, if their cytoplasms are going to grow, but without the nucleotides they can't divide, the answer is anytime you see low number of nucleotides, you're going to get megaloblastic anemia. You're going to get big cells where the cytoplasm is growing, but they're not dividing. You're going to get these these hypersegmented neutrophils. You're going to get this asynchrony, I like that. But anytime you see megaloblastic anemia, the cause of megaloblastic anemia is always going to be the fact that there are just a low number of nucleotides or Because without nucleotides, my cell can't divide, it can't differentiate, I can't finish the cell cycle. It's just going to grow and grow, but it's never going to quite finish. Not ideal. So no, if you can't generate usable tetrahydrofolates, your cells can't divide normally, you get megaloblastic anemia. Also makes sense in pregnant women. Pregnant women have a baby that's dividing from 1 cell to 2 to 4. Baby needs lots of nucleotides. Mom needs lots of folic acid so baby can have lots of nucleotides. And if mom doesn't provide the folic acid, baby can't divide correctly. I'm not surprised you might get some of these neural tube defects that may occur along the way because of this division problem, this lack of synthesis when you need it. Okay. Here's the other one, though. There are many versions of tetrahydrofolic acid. Do you think your test expects you to remember every individual tetrahydrofolate structure? In fact, the only one you have to really remember, or the only one I think you're going to have to really see on your exam, is going to be methyl tetrahydrofolate. And that's the leftover. That's what's left whenever you're done using folic acid. And to explain the methyl tetrahydrofolate, to explain its correlation to homocysteine, I think it's actually better than just to look at a table. Let's actually draw it out of it. So here's the thing. Folic acid needs to be activated to usable tetrahydrofolates. And there are many different versions of usable tetrahydrofolates. Why did we need usable tetrahydrofolates? Why do we need THF in general? Well, THF is going to be what we use as a base synthesizer. Tetrahydrofolates are going to be used to make thymidine and make your purines. They're going to make adenosine and guanosine. But here's the thing. Every time you use your tetrahydrofolates, every time you use that tetrahydrofolate, every time you make a structure, the tetrahydrofolate changes. Eventually, as you use the tetrahydrofolates to make these thymidines or make these adenosines or make these guanosines, every time you use the tetrahydrofolate to make something, you're damaging the tetrahydrofolate a bit. Eventually, you generate an unusable tetrahydrofolate because you've used it up. You have completely degenerated it into what's known as methyl tetrahydrofolate. So folates are usable in many forms, but once they get used, once their structure changes, eventually they're all degraded down to the methyl tetrahydrofolate, which you can't use. Not ideal. Now, here's my question. Do you really just think this methyl tetrahydrofolate, do you think it's worthwhile just to throw it out? Because we can't use it in its current form. Are we just going to throw it? No. The whole tenet of biochem, recycle, reduce, reuse. And in reality, the only thing that's stopping you from recycling that folic acid, the only thing that's keeping you from making more bases, the only thing that's keeping you from using that tetrahydrofolate again is that stupid methyl group. If only you could move that methyl group, and we can't. We're going to move it to homocysteine. Because again, where does homocysteine come from? It comes from methionine. We said methionine is a methyl donor. Methionine, which has a methyl group attached, donates that methyl group. We're going to give away the methyl group. We're going to use that to generate epinephrine, which we talked about yesterday. We're going to use methionine's methyl or CH3 group to generate the 5' methyl guanosine cap. And so we use methionine, we take its methyl group, and that's what creates homocysteine. Homocysteine doesn't have the methyl group, and that's what makes it dangerous. So this is literally 2 birds, 1 stone. I have this useless methyl or this useless CH3 on the tetrahydrofolate. Homocysteine needs a methyl group to stop it from damaging, stop it from killing, stopping from hurting. So question, what would you want to do to kill two birds with one stone? How can I make it so that my tetrahydrofolate is usable again while considerably decreasing the dangerous homocysteine? Let's move, let's transfer, let's donate that methyl group. The enzyme that transfers the methyl to homocysteine is known as homocysteine methyltransferase. You're going to take the methyl group and transfer it onto homocysteine. And so you can literally watch as the methyl group moves. We're going to take it off of the tetrahydrofolate and move it onto the transferase. By moving it off of the tetrahydrofolate, you can recycle it, you can reuse it, and therefore you can generate more nucleotides. Everyone's winning. Then I'm going to take that methyl group, put it onto homocysteine, because remember, homocysteine does not have a methyl group. Homocysteine is what is left after methyl donation. Methionine has the methyl. Methionine donates the methyl. And that's where homocysteine comes from. So by moving the methyl, taking it off of the tetrahydrofolate, we recycle, we can reuse it, new nucleotides. So we've recycled one of the birds. By putting it onto homocysteine, by regenerating methionine, you've recycled and remade methionine. You've moved the methyl and made two usable products in doing so. So win-win. So if there's no folic acid, and we'll use the red arrows to point out folic acid, if there's no tetrahydrofolates, we go back a step, that's fine. If there's no tetrahydrofolates, you can't make nucleotides, which is going to be your megaloblastic anemia, because with low nucleotides, a nucleotide means megaloblastic anemia. But if you're not making nucleotides, then there's no methyl tetrahydrofolate. There's no methyl group to move. So what does that mean for methionine? If there's no methyl to move, what happens to methionine? Yeah, if there's no methyl group to move, you can't regenerate. With no methyl tetrahydrofolate, there's no transfer. Methionine goes down because there's no methyl group made originally. There's nothing to move. You can't give it back. You can't generate methionine. So what's going to happen to homocysteine? If methionine goes down, that's because homocysteine can't get its methyl group. Homocysteine can't be recycled. Homocysteine goes up. That's why we get in B9 deficiency or folate deficiency, we end up with homocysteine because you can't recycle it. And that was because with no folic acid, there was no nucleotide production. There was no problem with the folic acid. Now you'll notice though, what other vitamin also tends to cause megaloblastic anemia? What other vitamin tends to cause homocysteine? It's B12. And you can see on this diagram why. If you want to move methyls, then B12 is a necessary component of homocysteine methyltransferase. B12 is literally what moves methyls for you. B12, the vitamin, loves a good methyl movement. So if you want to move the methyl, if you want to transfer the methyl, B12 is going to be what gains it and what transfers it. So in a cobalamin deficiency where there's no B12, you would expect, again, homocysteine methyltransferase wouldn't work. Without B12, you can't move the methyl. Methionine can't be recycled. Homocysteine can be recycled. Methionine down, homocysteine up. Looks the same because you can't move it. What's going to happen to usable folic acid if you can't move methyl groups? If there's no B12 to move the methyl, then usable tetrahydrofolates are also going to go down. Because if you can't move methyls, you're not going to be able to recycle. You can't get the methyl group off of methyl tetrahydrofolate. You can't get the methyl onto methionine, all bad. But I like where Akasha said, What's going to happen to the unusable folic acid? What's going to happen to methyl tetrahydrofolate? If you can't move the methyl group, if there's no B12, that's going to go up. That's really the one big distinction in this pathway between B9 and B12 is if there's no B9, there'd be no folic acid whatsoever. If there's no B12, you can't move the methyl, so you'll use up the folic acid, you'll make all this methylated mess, and you can't move it. Now, you tell me, when you do a question on step 1, or when you think about USMLE and B9, B12, how often have you seen a question mention methyl tetrahydrofolate as the distinction between them? Never. That's because B12 is used in other unrelated pathways. This is literally how B9 and B12 work together. B9 doesn't work anywhere else, but B12 works in unrelated pathways. So while in B12 and B9 are related, without B9, you can't make nucleotides, you can't recycle folic acid. Without B12, you can't recycle folic acid, so you can't make nucleotides, you can't make methionine. So while this pathway shows how B9 and B12 are related, B12 is useful in other pathways. Dare I say we go back to vomit to finish this off. Because while B12, like folic acid, is needed for homocysteine methyltransferase, used to recycle methionine, it's also going to be important in that vomit pathway. And we'll see why as we do part 2. Now, one distinction between B9 and B12 is who gets it. Patients who are going to be B12 deficient, of water-soluble vitamins, do we tend to store water-soluble vitamins? Usually not. We only really save B12. So B12, and that has to do with its absorption, right? B12 must be protected as it relates to intrinsic factor. B12 is hard. So we store B12 a little bit more. That's fine. But notice some people won't absorb B12. If you suffer from pernicious anemia, you have an autoimmune disease attacking the cells that would help you absorb B12. Also, if you have bacterial overgrowth or if you've had resection, if you can't absorb in the gut as easily, B12 eventually gets lost. If you have an intrinsic factor deficit, maybe a parasite deficient or parasite infestation, no doubt. Vegans also eventually become deficient in B12, but how long does it take before you see a vegan become deficient? That's going to be years, right? Like if I decide today I'm going to become a vegan for lunch, I'm not worried about B12 deficiency today because you store it. As long as your liver was able to store it, you have it available to you for a while. The one I would add to your list, though, the one that B12 is tested a lot in, is the elderly. Elderly patients, even though their diet may not change, their capacity to absorb from their liver and get usable B12 does a bit. So if you're going to talk about an elderly person, then that might be B12 deficiency. So if I'm stuck between B9 and B12, I'm thinking it could be the patient. If it's not the patient, then it could be the pathology. Because while B9 and B12 both lead to homocysteine because of a lack of recycling, while B9 and B12 both lead to megaloblastic anemia because of a lack of nucleotide production, B12 is unique in that you do get this neuropathy. And this is important because the neuropathy has nothing to do with B9. The neuropathy has nothing to do with tetrahydrofolates, nothing to do with nucleotides, nothing necessarily to do with the homocysteine. The peripheral neuropathy comes from the vomit pathway. And this is why we did part 1 versus 2. I want us to see it and be able to review it again. Of all the pathways we'll discuss, I think vomit today is probably the nastiest one. And I think looking at it in chunks makes more sense because then you can see how everything comes together. We said before that why do we even make prop-CoA? Why do we even generate this 3-carbon molecule? It's recycling. It's all about building. We ingest a lot of valine, but I can't use valine as just valine all the time. So our body recycles it to make it usable for other pathways. Because valine is just a sexy carbon skeleton. If I could recycle it, I'd be in the right position. Same thing with the 3 carbons of an odd chain fatty acid. Okay. Those last 3 carbons of an odd numbered fatty acid, let's recycle them into a usable form. Same thing with methionine. While methionine is useful, if you have excess, I don't want to waste it. So if I can't use methionine in its current form, let's recycle it into something I could possibly use. Same thing with isoleucine, same with threonine. The vomit pathway is just a way to take carbons in one form and transform them into another. So when you start the metabolism, while all these amino acids go through different metabolic pathways, they all eventually become prop-CoA. Can your body easily use propionyl CoA? No, we said this is kind of a useless molecule. So even though the goal of the vomit pathway is to turn these 5 molecules into a new useful form, it takes a few steps to get there before we're actually done with the recycling and making them useful. So we said the very first step was to make them useful, let's add a carbon. Our body's much better at using an even number of carbons than odd anyway, so let's use that. Let's add a carbon. What kind of enzyme is going to add the very first carbon? It's going to be that prop-CoA carboxylase. We said carboxylases all need A, B, C. They need energy ATP. They need biotin B from our gut bacteria and our diet. They're going to take a single carbon and add that carbon dioxide to your structure. And now you've made a 4-carbon chain. And honestly, that's usually better. Our body is traditionally better at even numbers than odd numbers. The problem is when you added that carbon, it became useless still. Because when you added that single carbon and turned 3 to 4, you put a methyl group on it, and that methyl group is useless. Now, here's the takeaway. When I say methyl and you're thinking vitamin, which vitamin should you immediately yell out? If I say methyl, if someone says methyl, you're going to say B12. Because here's the thing. What vitamin was needed to move the methyl off of tetrahydrofolate? What vitamin was needed for you to recycle methyl groups in the folic acid pattern B12? Guess what vitamin is going to be needed to move this stupid methyl group so you can finally stop the vomit and actually become useful? It's going to be B12. So notice we're going to have a slightly different enzyme. We're not transferring the methyl group this time. We're not taking it from vitamin B9 and giving it to homocysteine. So I don't need a transferase. Here, I'm just moving the methyl group, and that's done by enzymes called mutases or mutases. If all I'm doing is moving within one structure, then I'm just going to mutate it a bit. I'm going to move it a bit. We call it methyl malonyl-CoA mutase. And that's going to need B12 to move the methyl group. If you have B12 and you have the mutase, you will generate succinyl-CoA. You're like succinyl-CoA. Now question, is succinyl-CoA useless? No, this is incredibly useful. That is why the vomit pathway exists. You took these molecules in one form that you didn't need it, and by transforming them, you put them in a different pathway where I can make it all kinds of things. Succinyl-CoA can be used for heme production. Succinyl-CoA can be used in energy. We use it in the TCA cycle. Heck, you can turn succinyl-CoA back to glucose. So if I'm starving, valine may not be very helpful in its form, but I could turn valine back to glucose and I can prevent death and dying. It's a win-win. This is why the vomit pathway is important. Now, logically, it would have been much better if we found a way to do this quickly and didn't make all these poisons along the way. But we haven't evolved to that level yet. So the whole point of the vomit pathway is take these molecules in one form, transform them into succinyl-CoA in another form, and now you can use them as needed to make sure that you can compensate for whatever's going on in the world around you. That's the idea. So here's the thing. Imagine there was no B12. We already said before, if there's no B12, you'd have all this methyl tetrahydrofolate, because without B12, you couldn't move the methyl. What about in this vomit pathway? If there's no B12, what else would you see? In this pathway, if there's no B12, you couldn't move that carboxyl group. Grant, I keep calling it a methyl because I think that makes it easier for your test purposes. I think that makes it easier for our memory device, I'm being honest. But you can't move that carbon that was added. You can't move or generate that weird methyl structure. So you end up with lots of methylmalonic acid. Now, I've always liked calling methylmalonic acid, just to drive home why it's so poisonous. I like calling it myelin malonic acid. Because you know who tries to use methylmalonic acid but can't use it successfully? Your myelin. And what happens is when your myelin uses this, it disrupts signaling. It disrupts your myelin sheath. It disrupts conduction. And you end up with nerve issues. Long term, you end up with subacute degeneration of the spinal cord. But it all starts with that peripheral neuropathy, simply because the myelin is being affected by this myelin malonic acid. But notice, if it's a B12 problem, what were the molecules, or what did the elevated molecules have in common? In a B12 deficiency, what did the accumulated molecules have in common? In B9, it was methyl tetrahydrofolate that accumulated. In vomit, it's methyl malonic acid. When there's no B12, the chant I like is no B12. You're going to see lots of methyl products. And specifically, it's going to be methyl products that are useless in the form they're in. No B12, you get lots of methyl tetrahydrofolate. Useless, can't use it. No B12, you get lots of methyl malonic acid. Can't use it, useless. But that is a huge board clue to help you think if B12 is missing. B12 isn't needed for the good methyl groups, but it's needed to move the bad ones that are creating either toxic or useless, poisonous, problematic molecules. So the chant I've always liked for B12, I say B12, you say methyl movement. B12, methyl. You'll be amazed that if you see something with a lot of methyl attached, and you're like, I have no idea what that molecule is, or that molecule's not useful, it's almost always a B12 question. I say B12, you say methyl movement. That's the takeaway. So no matter which methylated product that accumulates, you know if it's a problem, that it was a B12 that was missing, we couldn't move. And that's also why we did vomit in two parts. I think it's easier to visualize. I think it's easier to visualize this. And to Riam's point, you're exactly right. If I give you B9, that would never help you with the neuropathy, because B9 doesn't help with the methylmalonic acid. B9 or folate doesn't help with the myelin sheath. Done, done. So while I think your test will primarily mention methylmalonic acid, I think it's easier just to say if I see lots of weird methyl molecules, that's probably because B12 isn't there to move it. B12 moves methyls. Win-win, done. Grab your point, done. Now, the last water-soluble vitamin, and we talked about this one ad nauseum, there's really nothing left to add to it, is vitamin C. Which C protein requires vitamin C? Yeah, I hear vitamin C ascorbate, I'm thinking collagen. In particular, we need it for prolyl and lysyl hydroxylase. You need it for hydroxyproline, hydroxylysine. That was going to be important for collagen hydrogen bonding. So without vitamin C, without the hydroxylase, without the hydrogen bonding, you have problems folding, you get weak collagen that causes the wound problems, the easy bruising, the bleeding. Without vitamin C, you also have bone issues in infants because you need vitamin C and you need that collagen normally if you want bones to develop normally in those infants. So a lot of the issues associated with vitamin C deficiency is because without C, you just get weakened collagen. The key is if you needed it early during bone development, or if you're later in life not eating your green leafy vegetables or whatnot. But I'd also say, and I know this is one, now you'll notice in many of these, I gave you more than your book did. Here's one, I took one out. I don't know, I should say, I've not seen a question about vitamin C and dopamine in probably 6 years of going back through practice. So I think these are the ones most important, explicitly probably collagen. There's never too much you can learn, but if we're looking for the most likely scenario, then I think prolyl and lysyl hydroxylase are more likely. The other thing, though, is without vitamin C, you lose iron. Because it turns out when you eat iron, you eat what's known as ferric or Fe3+. Now, Fe3+ is not absorbable. You can't absorb the iron that we eat. So what vitamin C does is vitamin C gives away a little electron. How many of you have heard of vitamin C as an antioxidant? Yeah. All that means is antioxidant, prevent oxidation or allow us to oxidize normal, give away electrons. And it does it to iron in your gut. Vitamin C gives away electron, vitamin C's happy. Iron goes from 3+ to 2+, and now you can absorb the 2+. So if you ingest iron and you want to absorb it, vitamin C needs to be there. No vitamin C, no reduction of the iron, you can't absorb it. So long term, you could end up with some iron deficiency anemia. And that has to do with the fact that without the vitamin C, I'm probably not absorbing the iron the way that I need to. And things like that. Now, that was a lot of vitamins. That was a lot of vitamins. And definitely there's more to vitamin C and its relations. I don't know if you'll ever get tested on more. I think with vitamin C, the USMLE is really fixated primarily on collagen, maybe the iron story, but we know vitamin C has all kinds of other responses out there. It can help you in urinary tract infections by messing with urine pH. You'll see a lot more of it in pharm, maybe a little bit in physio, things like that. But from a biochem perspective, connecting it to the pathways for biochem questions, to Daniela's point, to biochem questions is primarily going to be fixated on probably collagen. Although, like I said, in pharm, you'll talk about it with UTIs. In behavioral, you'll probably talk a little bit about it in protecting against certain drug abuses, things like that. But it won't be a biochem question. So we're going to focus on what I've seen biochemically mentioned, if that makes sense. So definitely not the only time you're going to see vitamin C. You're going to hear it quite a bit more as you go along. But I think it's worth our time to try a few questions, see what stuck, see what didn't. See how much better we feel about it. Question number 1. You guys don't need me. What vitamin's missing here? Yeah, you're missing B2. Why B2? Why is it riboflavin? And I love the chat stories like riboflavin. I gave you everything I could about the head, right? Now I could have put all kinds of other symptoms, but the fact of the matter is I see there's a rash, dermatitis on his eyebrows, his nasolabial folds. I see scalp related dermatitis. I see his throat is affected, which we didn't mention, but that's fine. He's got a discolored tongue, we did mention. I see cracking of the lips. I see peeling at the corners of the mouth. This is all about mouth, head. I bet if I looked, he might eventually develop some corneal neovascularization. He might be anemic. But again, we see a lot of face-related things. That's where your mouth is. Mouth is where your tongue is. Tongue is where the flavor is. It's riboflavin. And you guys were already picking 90% answer choice C. You, like I said, when I say you don't need me, you guys got it. You're on your way. You're out the door. Done. Had it been thiamine pyrophosphate, that would have been a B1 deficiency. And B1 would cause Wernicke-Korsakoff or beriberi, but it wouldn't have caused this one. Where does coenzyme A come from? That would have been a B5 deficiency. We put no pathology there. We said as long as you eat food, you should get B5, but it was always tested for CoA or pantothenic acid. Where does the niacin adenine dinucleotide nicotinamide? That's B3. And that would have led to dermatitis, diarrhea, dementia, but it would not have led to just the face. And if you had a trouble with methylcobalamin, that would have been B12. We would have seen homocysteine because you couldn't move methyl groups. We would have seen decreased folates and megaloblastic anemia because you couldn't move the methyl. We would have seen neuropathy because of methylmalonic acid. But this one, you guys handled perfectly. Let's step it up a bit. Try question number 2. Okay, now I wanted to surprise you a bit. I know you're all expecting vitamin questions, but since our last set of questions, we also talked about toxins. And I want to get you used to the idea that on your exam, it's not just going to be here's all the biochem. We got to integrate it a little bit. I do that as we go further and further. I want to make sure we're thinking about everything in total because now we've covered over half of the biochem book and still have more hours than we started with. That's a win-win. Yeah, we're going to diagnose this patient with whooping cough. We see that she's got a low-grade fever, originally an irritating cough. The cough has persisted even though the other symptoms went away. I see that she turns purple during coughing. She's got a strange whooping sound. I think it's pertussis. Okay. Now the question about this pathogen, or the question is about its toxin, pertussis toxin. What is the target of pertussis toxin? The target is GI. Perfect. And what happens when you ribosylate or modify GI? What was that memory device we said? You inhibit the inhibitor. Basically, we're going to block GI, which means what's going to happen? If you inhibit the inhibitor of signaling, if you take off the brake, you're going to see more signal. You'd expect more cyclic AMP, which wasn't listed. But 64% of you said you'd also pick that with more cyclic AMP would lead to an increased activity in protein kinase A. Without a doubt. Notice phosphodiesterases are enzymes that mess with second messenger signaling. They can mess with cyclic AMP, but they're not the target of the toxin. We're not targeting the enzymes downstream. We targeted explicitly the G protein itself. And B was a bit of a trap here because you might have anticipated that you targeted GI, thought let's inhibit. But we said that if you target the GI, you inhibit the inhibitor, you would increase adenylate cyclase, not decrease. We also say anthrax toxin itself can increase adenylate cyclase. It wasn't a ribosylator, but anthrax toxin or edema factor was adenylate cyclase under no control that was allowing us to signal normally. If anything, you might see more gene expression because more cyclic AMP would lead to more activity of that transcription factor CREB, that leucine zipper protein that was going to turn on genes in response to water-soluble hormones. And if you wanted to mess with calcium release, you wouldn't have gone after GI, or heck, you wouldn't have gone after GS. If you want to target a G protein and mess with calcium, you would have targeted GQ. But none of the toxins we discussed so far had anything related even remotely to GQ. So you guys handled this one perfect. And you know me, I love taking questions right after the break, and it's exactly 9:30 here on the West Coast. It's 12:30 on the East Coast. We've got 2 hours to go. We're going to finish our vitamins, start the big picture at the end of chapter. We're going to be right on time, but let's go grab a snack, use the restroom, and when you come back, we'll do question 33. Nice job on these questions so far. Let's keep it going. See you after.